Now this problem is for vertical separator. Okay, these dots. So can we calculate size and heat requirement of a vertical heat radiator settling coalescing section. Okay, this section you have to calculate. So vertical separator means you will have settling section H also, right? So oil flow rate now is changed to 1200 BPD so that you can get different calculation. Inlet BSW same we have kept, outlet BSNW 1%, oil specific gravity same, oil viscosity also same parameter we have taken here, water specific gravity same whatever you have taken for horizontal separator, specific heat 0.5, specific for heat for water 1.1, inlet temperature 85, retention time 20, treating temperature for 105, 125 or no heating. No heating means operating temperature you are using. Okay, inlet fluid is not heated, only 85-degree temperature is maintained. Okay, so examine what I should write. Assume oil viscosity like 105, 125 and 85, like 85, 40, 125, it should be like 125. Okay, so higher temperature viscosity be lower. Okay, heat loss 1%, 10% we are assuming. Okay, the same procedure you have to follow as horizontal separator, but the formula is different. Okay, so formula, please don't mix up the formula. So for T equals 185 degree Fahrenheit, D square 6690 QO mu O SG del SG dm square. Okay, now you put the values 6690 into 12,000, mu O for 85 degree is 45, it is given there. Okay, and SG del SG we assumed in previous problem that del SG is not changing although we are changing temperature. So 0.2 it is fixed. And what about your dm? Dm value also you see the previous problem actually. So dm will be coming like 200 mu power 0.25. Okay, so 200 into mu means 45 for 0.25. Okay, so this will be coming 518. Okay, micrometer. So this is dm, this formula 200 into, okay, so 518. So this value is coming 6731.7, and this is d square, so it will be inch square. Okay, similarly you are calculating for 105 degree Fahrenheit, you are calculating d, this is d square. Okay, so d square, so d you get 82.46 inch. Okay, now for 105 degree you are calculating again same thing, 6690 1200 into 20, your viscosity changed, and your 0.2 your del SG not changed, and dm value how to calculate? dm equals 200, your viscosity 20 power 0.25. Okay, so this will give 423. So total value is coming 4487.8. This is d square actually. So d will be coming as 67 inch. This is inch square because square term is there. And for 125 degree, d square equals 6690 1200 again into viscosity again change to 10 and 44, sorry, not 44, this is 0.2 into dm value. So dm equals 210 power 0.25. So this will be giving not 4, this is 356, 356, so 356. Okay, so this is giving 3173 inch square, so D equals 56.3, sorry, 56 inch. Okay, go to next slide. Space not there. You're writing? Okay. Okay. Now we'll go to retention time based calculation. Retention time based calculation, you can remember d square h equals formula TRO retention time flow rate divided by 0.12. So this is 20, flow rate 1200 is 1200, right? Okay, 1200 then 0.12. Okay, so this will be giving 205800 inch square. Now again you have to draw the figure. H actually this coalescing section height. Like so this one coalescing section, this height is H. Okay, so this will be coming like this, and values are like 20, 200, 20, 200, and then 40, 60, 80. Okay, and diameter, this is H in inch, this is dia or D in inch. Okay, these values are 20 to 90, so 20, 30, 40, 50, 90. Okay, this is retention time based calculation. So this formula retention time based means d square h equals 205800. Okay, so this, so d or h, if you put h value, h equals 205800 divided by d square. So this is your curve from here. Okay, and other curves, like it will be like this, T equals temperature, T equals yeah, so capital T I am using, this is temperature, small t I am writing for time. Okay, so this is temperature, so temperature 125, so other temperature also will be like this. Okay, now this is again infeasible zone. Okay, this lower portion of your retention time curve is infeasible zone, so upper portion you can go, or on the curve also if you take some data, that will be okay, because you have many DLF calculations, so you have to take some optimal value, and you can say this is optimal, it is satisfying all the norms, and you are calculating. Okay, now we'll go for heat calculation for this one. How much temperature, how much heat will be required. So heat calculation, again the same formula you apply, 1 by 1 minus L 15 QO del T gamma O CO plus water percentage, gamma water, C water. So formula will be like this, 1 minus 0.1%, 10%, so 0.1, 15 QO, Q is 1200, delta T, again we are assuming 105 degree optimal temperature in for heating, 105 minus 85. Okay, gamma O 0.86 into 0.5 plus omega value, I will write here below because my picture will come, 0.5, 0.15 means this is percentage of water, BSW 0.15, then 1.06 and 1.0, 1.1 is your specific heat of water and 1.06 is specific gravity of water. Okay. So, finally, this data is giving 241,960 BTU per hour. Okay. So, this much of heat will be required for heating your system 85 to 105 degree centigrade temperature. Okay. And with 15% inlet water is there. Okay. That water will be separated during this separation process. Okay. Thank you very much for this horizontal separator calculation. Okay. I will give one problem, I will not solve you, you can try to solve. Okay. The problem is like this. It is given in your K. Arnold book volume 1. So, oil gravity is given 30 degree API, okay, and 0.875 Sg specific gravity. Oil flow rate is given 5000 barrel per day, BPD, inlet temperature inlet equals 80 degree Fahrenheit, water specific gravity 1.06, 1.04, inlet BS and W 10%, outlet BS and W 1%. Okay. So, in this case, actually in the book temperature is not given, viscosity is not given for different temperature. So, in that case you can use the chart, I can give, okay, use that chart, maybe I will give the chart also. So, from that chart you can find the value of viscosity and you can calculate the viscosity. Once you get viscosity, after that only you can calculate D, particle size is not given, dm. Okay. Then the steps is that first you get viscosity data, from formula you can collect or use chart. Once viscosity you got, then dm formula you apply, 200 mu per 0.25 within that range. Once dm you get, then you can get d LEFF, okay, d square LEFF, okay, this parameter you can get. Once you get this parameter, then you draw the curve. Then from that curve you say this is the infeasible region and my feasible design can be one design, you can say, okay, this can be one design. Okay. You cannot say too high or too long LEFF or too long or too large diameter. Okay. So, you have to take, let us say, some value within this range. Okay. So, if you are taking, let us say, here, so this may not help, it will be too large diameter, okay, or you can go, you are going upper side. So, that is also not helpful. So, you should take here where curve gradient is high. Okay. This will be maybe your optimal zone. So, in that zone your diameter and LEFF will be optimal, fine. And accordingly you can calculate heat also, heat formula again you can remember that 1 by L by del 15 into QO, that formula you can use and you can calculate the heat. So, for horizontal and vertical, for both cases you should practice. Okay. And many times I do not give direct formula whatever you are using, maybe step by step I will ask. So, in that case actually you have to remember the derivation procedure of the formula. Okay. If you are not remembering only final one, then maybe some derivation in some step I will give, okay, calculate this one. Okay. So, then in that case you will face difficulty if you remember only the final one. So, better you remember the derivation step by step how the formula came up, then you give the calculation result. Okay. If you are giving for written exam in a class, in your course exam, so in that case maybe I can ask, okay, give step by step calculation, show this one values. Okay. But if you are going for NPTEL or online exam mode, so in that case I will be asking final result, but maybe based on some steps, not on the final result. Okay. So, whole thing you have to remember final also and you have to remember steps also, and how to solve the problem step by step you should remember. Okay. 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 Thank you very much for this one.